afternoon to you. We are going to continue the repeated eigenvalue. Okay, for the 3 by 3 homogeneous system, where this is the third case where we have 3 by 3 system, but we get 3 repeated eigenvalues, means 3 same eigenvalues, which give only one eigenvector. For example, solve this y prime equal to 1, 1, 1, 2, 1, negative 1, negative 3, 2, 4, 1. To solve this homogeneous system means we want to find what is a vector y here. And this is actually in the homogeneous system y prime equal to a1, where the matrix A is actually 3 by 3, 1, 1, 1, 2, 1, negative 1, negative 3, 2, 4. To get the solution for this homogeneous system, we assume the solution y is actually equal to eigenvector t multiply exponent lambda t. This will lead to actually a homogeneous system A minus 2i, A minus lambda I v equal to 0. Solving this homogeneous system to find the eigenvector, and then to get the eigenvector, we must get the eigen's value. If we have a 3 by 3 system, then we have 3 eigen's value. To get the eigenvalue, we need to let the determinant of A minus lambda I equal to 0. We need to get the lambda, we need to let determinant of A minus lambda I equal to 0. First step, find what is the A minus lambda I. So matrix A is 1, 2, 3, 1, 1, 2, 1, negative 1, 4. So minus with lambda. If A is 3 by 3, your I is identity matrix will be 3 by 3. This is A minus lambda I. And then we will have so now this is A, this is already lambda multiply I, so it changes on the main diagonal only. Now it takes A minus lambda I, hence we only having changes at the diagonal. So it will be 1 minus k. So next round for A minus lambda I, you just need takes a matrix A minus with lambda at the main diagonal. So 1 minus lambda is the entry below the diagonal, and upper the diagonal there's no changes. So the main diagonal is 1 minus lambda. This is 2, 1, so 4 minus lambda. So means to solve the homogeneous system, we let the solution is actually y equal to eigenvector v exponent lambda t. Will arrive at the homogeneous system A minus lambda I v equal to 0. And then to find the eigenvector, we need to get the eigenvalue first. To get the eigenvalue, we let the determinant of A minus lambda I equal to 0. So we find what is a minus lambda I. So the a minus lambda I will be here. So this is a, and then this one is actually a minus lambda I times a 2. Okay, when we ask it why, if you assume, okay, I think y equal to v exponent lambda t, you arrive to the equation a minus lambda I v equal to 0. Because you have the y prime equal to a1. So first, if you find y prime will be lambda v exponent lambda t. Then you have actually y prime equal to a1. Plug in the y prime here is actually, you have lambda v exponent lambda t. Y, we assume the solution is actually v exponent lambda t. Okay. And then we collect together these two terms. That's why you have a minus lambda, because a is a matrix, so lambda must be multiplied with an identity matrix. Okay. We cancel out both exponent lambda t. Okay, this is actually 0. That's why if you assume the solution is actually y equal to, y is actually v exponent lambda t, we arrive at the homogeneous system a minus lambda I v equal to 0. And then to get the solution, you must find the eigenvector, eigenvalue. Okay. So first step to find the eigenvalue, let the determinant of a minus lambda I equal to 0, because v cannot be equal to 0. So the only possibility is to let the a minus lambda I equal to 0. Determinant of a minus lambda I equal to 0. Okay, and here we show how to find the a minus lambda I. Okay, this is a matrix A minus lambda. Because here why we did initially, we have here this one. We cancel exponent lambda t, exponent lambda t. We have ab minus lambda v. We cannot because this is constant, this is matrix, so you must make it the same dimension. So multiply with our identity matrix, so that you can do the operations. So a minus lambda I. Quickly, you can next time you can just do take the matrix A, you minus with lambda at the main diagonal. Okay, and then to find the eigenvalue, you let the determinant of your, so now this is a minus lambda I v equal to 0. Okay, we already assume the solution is the eigenvector v multiply exponent lambda t. So you must solve the lambda. Okay, and this homogeneous system, eigenvector v cannot be equal to 0. So the only possibility is to let determinant of a minus lambda I equal to 0. Okay, that's why the next determinant of a minus lambda I equal to 0. So this is the determinant of the a minus lambda I. Remember, a at the main diagonal, you just minus with your lambda. Okay, now this is a determinant of 3 by 3. Okay, remember, to calculate the determinant of a 3 by 3 matrix, we must consider the sign. Start from this cell A11, which is positive, and then negative, positive, negative, positive, negative, alternate, positive, negative, positive. You may take any rows of any columns, and then multiply with its corresponding signs here. Okay, normally you take the rows or any columns that which consist more 0. Okay, in this case we don't have any row or any column that consists 0. So we take any rows that consist or any column that consists 1. So we take first row in this case. Take first row because 1 easy to do the multiplications. Once this one, I will consider first row. Okay. First of all, I take the first row, first column. So you just cross your first row, first column. So we have here. Okay, this cell, the sign is positive. So 1 minus lambda. Okay, and then after you cross the left, okay, this is a determinant of 2 by 2 matrix. Okay, 1 minus lambda. So this is 2, this is negative 1, this is 4 minus lambda. Okay, second sign, okay, second value here, because I'm considers the, okay, I'm taking the first row. So later on, okay, will be the second cell here. First row, second column. Okay, this sign is negative. Negative times 1 will be negative. Okay, and you left these two determinant, okay, of 2 by 2. And you got this is 2, negative 3. So negative 1, 4 minus lambda. Okay. Now go to third column. This sign is positive. So just okay, so plus 1. We left determinant of this 2 by 2. So 2, negative 3. So 1 minus lambda. So this is 2. And let it equal to 0. Then you simplify the determinants here. You have 1 minus lambda. Okay, remember how you calculate determinants. You take the main diagonal, product of the main diagonal, the main diagonal deduct with product of the other diagonal. So you got here 1 minus lambda times 4 minus lambda. So minus with product of this diagonal, so minus with negative 2 become plus 2. So now this one got negative. So 2 multiplies 4 minus lambda. So minus with this is positive 3. So minus 3. And then this is plus. So you got 2 times 2 plus here. 2 times 2, 4. So minus with this negative, so we plus 3 times 1 minus lambda. Then equal to 0. Okay, you expand and simplify it. Hence, you do it straight, you have 1 minus lambda. You expand these two factors. So you have 4, 1 times 4, and then negative lambda, negative 4 lambda, so negative 5 lambda. So negative lambda times negative lambda, so plus lambda squared plus 2. So expand the second bracket here. So I got here 8 minus 3, so I have 5 minus 2 lambda. So 4 plus 3 here, I have 7. So minus 3 lambda. Plus 3, 7, so minus 3 lambda equal to 0. Okay, I still need to expand this one. 1 minus lambda. So 4 plus 2, this one we got lambda squared minus 5 lambda plus 6. So minus 8 on this one. We collect these two together. Minus 5 plus 7, so I got plus 2. So 2 lambda minus 3 lambda, so minus lambda equal to 0. 5 plus 7, so 2 lambda minus 3 lambda minus lambda, and then expand this one. So 1 times this one, we have lambda squared minus 5 lambda plus 6. Okay, minus lambda multiplies here. So minus lambda cube plus 5 lambda squared minus 6 lambda plus 2 minus lambda equal to 0. So we got minus lambda cube lambda squared plus 5 lambda squared. Okay, after you got plus 6 lambda squared. So minus 5 lambda minus 6 lambda. and then minus 1 more, so minus 12 lambda. So 6a plus 2, so plus a equal to 0. Okay, and then I will next this one become positive by multiply both hand side by negative. I got lambda cube minus 6 lambda squared plus 12 lambda minus 8 equal to 0. Okay, and this stage you may use your scientific calculator to get the roots. So in the equation modes, okay, you got the want to find the root of the polynomial equations. So number 2, degree, you got degree 3. So key in the coefficients of your cubic equation. Okay, cubic term is 1, quadratic term is minus 6, linear term is 12, constant term is negative 8. Is x equal to 2. So it goes back. So this is an input for the polynomial equation. So mean in this case you get only one roots only. Okay, you may press I think shift. Since it only one roots. If you use your you can use your handphone to scan the QR code and the graph will be plotted on your handphones. So this case you have only one same roots. Lambda 1 equal to lambda 2 equal to lambda 3 equal to 2. Because cubic you should have three roots, but the calculator gives you 1 and you have confirmed it through the graph is only one roots. So you got 3 same eigenvalue. So step 2, we already find 3 same eigenvalue. So we are going to determine the first eigenvector v1 from a minus lambda I v1 equal to 0. And first our lambda is actually 2. And remember a minus lambda I, as I said, you just take the minus a lambda at the diagonal. So this is originally this is a. So minus the lambda 1 which is 2 at the main diagonal. Okay, this one. Okay, so you have 3 equations with 3 unknowns. Okay, 3 unknowns. You can try to use your scientific calculator to see whether you get 3 unique solutions. So again, I go to the equation modes. Okay, the simultaneous equations, 3 unknowns. Okay, for this calculator, you can solve up to 4 unknowns, 4 simultaneous equations. So you key in the coefficient of your simultaneous equation row by row. So start from negative 1, 1, 1. Right hand side 0 here stands for 0 vector. So it's 0. Okay. Second row 2, negative 1, negative 1, 0. Okay. Third row start from negative 3, 2, 2, 0. Okay. Before you press check, okay. Right hand side 0 vector, coefficient of z 1, negative 1, 2. Coefficient for y 1, negative 1, 2, go left. Coefficient for x negative 1, 2, negative 3, and then you see they give you infinite solution. So mean this homogeneous system you can get the unique solution, but you have infinite solution. Okay, infinite solution here means here we have 3 unknown with 3 equations, but actually you can reduce it to maybe 2 or 1 equation only. That's why you got infinite many solutions. Okay, to do this, okay, I observe, okay, we are going to reduce the entry A21, A31 become 0 by using suitable row operation. Okay, but there's no changes on row 1. No changes on row 1. No changes on row 1, but I'm going to eliminate A21, A31 become 0 using suitable row operation. And I observe this value is negative 1. Okay, so if I multiply by 2, and then, okay, I will get negative 2. So negative 2, I add up with 2, you get this, okay, 8-1 become 0. Okay, but we cannot only do for this cell, we must do for the whole row. So that's why this is called row operation. Okay, and the formula is exactly 2 times of row 1, add up with row 2, put the changes on your row 2. Okay, so we do the operation slowly for you to see. 2 row 1 multiply 2 times row 1, so this is negative 2. We got 2, 2. Okay, the right hand side with 0 like this. Okay, and then 2 times row 1 add up with row 2, to add up with your row 2, which is 2, negative 1, negative 1, 0. And then you add up. So negative 2 plus 2, 0. Because we add up here 2 times row 1 plus row 2. 2 minus 1, 1. 2 minus 1, 1. 0 plus 0, 0. And mix these changes on row 2. There's no changes on row 1. So row 2, 0, 1, 1. Okay, this is manually. Okay, you may also use your calculator. Go back to 1. Because actually it's the same operation, but we repeat 3 times for 3 columns, right? So what I'm going to do is the R1 in the R1, I will replace it as A in calculator, R2, B in the calculator. Then input this formula, ask a calculator to compute it 3 times by inputting back value of this is A, B. And because we already represent the row 1 as A, row 2 as B. So this is a A value, this is a B value. So we calculate it, repeat it 4 times. The last one only and 0, of course you get 0. You get this value. So it show you here. So 2 alpha A plus alpha B. Then you calculate. Okay, for first column, your A is negative 1. A is row 1. B is 2. So you get here. Result of first column is 0. Okay, this is put in the formula in calculator. This is manually. Because you repeat it, column 1, column 2, column 3, column 4, because both are 0, no need. So you calculate again. Now A is 1, B is negative 1. So you get result is 1. Okay. Column 2 and 3 actually same. So that's why you get same result, and this is 0. Okay, this is using calculator. Okay, if you don't like the calculator, you may do it manually. Okay, but the calculator will help you, especially if the value in a matrix A is not integer number, but it's a floating point number. So using the calculator will help you to calculate it quickly. Okay, now we have successfully we eliminate the cell A21 becomes 0. Now we are going to eliminate the cell A31 become 0. This one first. We are going to put this one become 0. We are going to makes this cell become 0. So this is negative 3. So this is negative 1. So if I find by negative 3. So negative 3 times negative 1, we got 3. So if I add up, so 3 add up with negative 3, I will get 0. That's why the operation is negative 3 times row 1 plus row 3. So here it's negative 3 row 1. In row 1, the whole row 1 multiplied by 3. So this is 3, negative 3, negative 3. So add up with row 3, which is negative 3, 2, 2. So add up together. Negative 3 row 1, add up with row 3. Put the changes on your row 3. So 3 minus 3, 0. Negative 3 plus 2, negative 1. Negative 3 plus 2, negative 1. Plus this 2, 0, 0. So make these changes on the row 3. Okay, after this two row operation, you notice that actually row 3 here is a negative of the row 2. Negative. So mean if row 3 here you multiply by negative 1, this becomes positive 1, positive 1. So row 2 and row 3 are actually equivalent, or you may cancel out the row 3. Or you may use the row operation. Let's say you take row 2, add up with row 3, put back your changes on row 3. So there's no changes on row 1, 0. No changes on your row 2. Okay. After you add up these two, 1 minus 1, you got 0, 0, 0. That's why from 3 unknown with 3 equations, we reduce to only 2 equations. That's why you got, okay, the calculator give you infinite many solutions. Okay, if you don't want to use the row operation, you can easily say, okay, if we multiply by negative 1, this is positive, positive. So row 2 and row 3 are actually same. You can delete it like this one, nothing, 0. So it just left 2 equations. Okay, from these 2 equations now, then you read back this, okay, 2 equations. This is negative x plus y plus z equal to 0. Second equation, you got y plus z equal to 0. Okay, solving these 2 equations, you will have, okay, plug in y plus z equal to 0 here. And plug in here. So you have negative x plus 0 equal to 0. Answer x equal to 0. Okay, and then from your y plus z equal to 0, okay, if I let here, if I let y equal to s, so s plus z equal to 0. That's why z equal to negative s. We put back the x, y, z. X they obtain is 0, y is 1s. Here, z equal to negative 1s. Okay, by letting s equal to 1, once you find the eigenvector 1, v1 is exactly 0, 1, negative 1. Okay, eigenvector 1. Step number 3, find the v2 from a minus lambda I v2 equal to 1. Because this is repeated eigenvalue. We have seen in here repeated eigenvalue for the case of 2 by 2 system. So to get the v2, so a minus lambda I v2 equal to v1. So similarly, this one. Okay, in step 2, a minus 2i v1 equal to 0. So this is equal to v1. They obtained in step 2. Okay, so a minus 2i v1. Okay, simplify, you get here. The difference is here. Step 2, this is 0 vector. Step 3, this is equal to v1 that you obtain. You get your v1, v2. You get the vector what is the x, y, z here. So similarly, using the previous same operation, in 2 row 1 plus row 2 put into row 2, because we want to eliminate this cell become 0. Okay, so we do it slowly. So 2 row 1, so negative 2, 2, 2, right side 0, add up with your row 1, which is 2, negative 1, negative 1, 1. So you add up 0, 2 minus 1, 1, 2 minus 1, 1, 0 plus 1, 1. Chooses here. This one you got value. Previously, step 2, this is 0. Okay, now to make this become 0, you multiply row 1 by negative 3, add up with row 3, put back the changes on row 3. Now, we observe equation 1, negative 3, row 1. So this is a positive 3, negative 3, negative 3, right hand side 0, add up with the row 3, which is negative 3, 2, 2, negative 1. So add up together. So 3 minus 3 is 0, negative 3 plus 2, negative 1 is negative 1, negative 1. So this is the latest row 3. Put it here. Okay. And then, okay, against as just now, you can see this one, row 3 is actually multiple of row 2, or you multiply it by negative 1, then we get this is positive 1, positive 1. So row 2 and row 3 are actually similar. You can reduce to only 2 equations, or you may use the row 2 plus row 3 put into row 3. Then, okay, there's no changes on your row 1 and row 2. These two rows add up. 1 minus 1, 0. So that's why you reduce to only 2 equations. Reduce only 2 equations. Okay. And then from these 2 equations, okay, you can read back this negative x plus y plus z equal to 0. Negative x plus y plus z equal to 0. And then from second equation, y plus z equal to 1. So the difference with the step 2 is here. Step 2, y plus z, this is equal 0. So you plug in y plus z equal to 1 here. So you have negative x plus 1 equal to 0. That's why your x equal to 1. And then from y plus z equal to 1, okay, for repeated eigenvalue, it's very important. In step 2, you make assumption y equal to s. Make y equal to s. So here you must consistent to let the y equal to s. Must same consumption only for repeated eigenvalue. So y equal to s. So z equal to 1 minus s. So put in y, x is 1, y is s, z is 1 minus s. Break it into a constant vector and a vector dependent on s. So x is only constant, 1 plus 0s. Y is no constant, so 0 plus 1s. Z is 1, constant is 1, okay, negative 1s. Okay, the constant vector will be v2. This is v2, and this is actually your v1. Okay, check that. 1. Okay. So this one we use a minus lambda I v2 equal to v1, 0, 1, negative 1. So this is your 1. So this is a y2. In the solution, you have a y1 plus b y2. Y2, you have actually okay, the v1, v1 repeated, so multiply by t exponent 2t plus v2 exponent 2t. Okay, now we are going to find the v3, the third eigenvector. Okay, so the new things, a minus lambda I v3 equal to v2. So v2 that you obtain in step number 3. Here. 1, 0, 1. So the left side same with the step 2, step 3. So this part same because a minus we have the same eigenvalue. So 2. So this part is v2. So against to this one actually, if you key into the calculator again, we get infinite many solution. So that's why it shows you 3 equations. You can actually reduce to 2 or 1 equation. Okay, so you got infinite many solutions. So you use the same operation, which is 2 row 1 to add up with row 2. So this negative 2, 2, 2, this is 0. So 2, negative 1, 0. So this one is 1. So you add up together. Negative 2 plus 2 you got 0. 2 minus 1, 1. 2 minus 1. So 1 add up with 0. So you got the second row. 0, 1, 1, 2. Okay. Sorry, got this one 2 times. So 2. So 2 add up with 0, 2. So it's 0, 1, 1, 2 for second row. Put up the changes on row 2. So 0, 1, 1, 2. Okay, for the third row, okay, we have the same, actually the same operation for A31. So it's negative 3, row 1 add up with row 3. So row 1 minus by negative 3. So this positive 3 is negative 3, negative 3. So it's negative 3. Add up with row 3. Row 3 here, negative 3, 2, 2, 1. So you add up together 0. So minus 1, negative 3 plus 1, minus 2. So the new new changes on row 3 is 0, negative 1, negative 1, negative 2. 0, negative 1, negative 1, negative 2. So again, you can see row 3 is actually multiple or negative of row 2. You can cancel, or you use row 2, you add up with row 3, you put up to row 3. No changes on your row 1 and row 2. Okay. Row 2 add up with row 3. So 0. 1 minus 1, 0. 1 minus 1, 0. 2 minus 2, 0. That's why reduce to only 2 equations. Then read back from the first 2 equations. You have actually negative x plus y plus z equal to 1. Second row, y plus z equal to 2. So the difference compared to this step 3, okay, this one no longer 0, this one no longer 0. Okay, when finding the eigenvector v2, this is 0, this is 1. So a little bit changes. So now plug in y plus z equal to 2 here. Okay. So you have negative x plus 2 equal to 1. So means that x equal to 1. And then from the y plus z equal to 2. Okay. Again, for repeated eigenvalue, in finding v1, you let y equal to s. Finding v2 also you must let y equal to s. Finding v3 also you must have the same assumption, y equal to s. Okay, you must have same assumption, otherwise you won't get the nice pattern here. So s plus z equal to 2. So z is 2 minus s. Plug in. X is 1, y is s, z is 2 minus s, break into the constant vector and a vector dependent on s. So x is only 1, no s. So y is only s, no constant. Z you got constant 2, s is negative 1. So the new constant vector will be your v3, and this will be always your v1, provided you have the same assumption. From finding v1, you will let y equal to s, v2 must also y equal to s, v3 must also y equal to s. Then you get this nice pattern. Constant vector is always your new eigenvector. A vector dependent on your s is always your v1. And the y3 exactly, okay, V3, you multiply exponent lambda t, lambda is 2. V2 is exactly V2 times t exponent 2t. V1 now is t squared over 2 exponent 2t. Because our general solution is a y1 plus b y2 plus c y3. So this is a v1 exponent 2t. This is what I call as y1 plus b v1 t exponent 2t plus v2 exponent 2t. Okay, plus c v1 now is t squared over 2 exponent 2t. v2 is t exponent 2t plus v3 exponent 2t. Okay, or you may collect it together row by row. We collect together all the a times 0 exponent of first row, a times 0 exponent 2t plus, collect all first row together, second row together, third row together. Okay, so this is for 3 same eigenvalue. So I repeat, for 3 same eigenvalue, first you find the eigenvalue as usual, and then you find the first eigenvector. You find the eigenvalue is actually determinant of a minus lambda I equal to 0. Okay, later on you find the a minus, got 3 same eigenvalue. So it's lambda a minus lambda I v1 equal to 0. To find the v1. To find the v2, you let a minus lambda I v2 equal to 0. Equal to v1. To find the lambda 3 v3, let v3 equal to 2. So this for 3 same eigenvalue. With this, thank you for attention.